Hello guys, welcome back. So we are having the DSP classes and we'll start a new module today. It is about the filter realization. That means through hardware how you can implement the filter. So for hardware design, whatever we are doing, that we are saying that filter structure. So here in this lecture we will try to cover the FIR filter structure or FIR filter realization. This entire module we have divided into 6 lectures. 2 lectures will be on FIR filter realization. So in this lecture we will be covering the direct form and linear phase realization of FIR filter, whereas next will be the cascade form realization of FIR filter. Then for IIR filter we shall have 4 lectures. One is on direct form 1, then direct form 2, and then cascade form and parallel form. And in all the lectures we will try to understand these concepts with the help of some numerical examples as well. So to start with the FIR filter realization, here mainly there are two types: direct form realization and linear phase realization. Direct form realization is also known as transversal structures. Now here the basic concept is used, the time delay principle of Z transform, that is the Z transform of x of n minus 1 is Z inverse x of Z. So this concept we are utilizing, and we are using this Z inverse as the digital element as unit delay element. So unit delay element, we know these are the unit memory elements also. So if we try to implement the filter circuit, digital filter circuit, that means here we'll have to use some unit memory element, that is your shift register or flip flop. So that kind of thing we'll be using, and we'll be requiring adders. So this is the symbol of adder, and this is the simple symbol of the multiplier. That means the filter coefficients, the weights associated with each of the polynomial that will be given by this particular symbol. So the concept is that if we are using one unit delay element, and here if we have the input as x of n, so at the output we will be getting x of n minus 1. So this concept is implemented like this. And also in FIR filter realization we have multiple delay elements. So this particular line, say after 1 unit delay, here we will be having x of n minus 1, then 2 unit delay we will be having x of n minus 2, and so on. So here we will be getting x of n minus 1, capital N minus 1. So this particular line we name as the delay line. So this is a very important concept, because FIR filter realization later on we'll be seeing that we are tapping out the signals from this line. So FIR filter many a times also referred as tapped delay line filter. So same thing, instead of using FIR filter, this term also used in many places, that is tapped delay line filter. So now for direct form or transversal form realization, let us consider the system function h of z, which is nothing but summation n equal to 0 to n minus 1 h of n z to the power minus n. So h of z is nothing but the ratio of y of z and x of z, and if we expand this summation, what we get is h of 0 z to the power 0, so that is 1, so we have not written it here. Then h of 1 z inverse h of 2 z to the power minus 2, and so on, it will go up to h of n minus 1 z to the power minus n minus 1. So now if we cross multiply it and take z in this side, right hand side, so what we get, y of z equal to h of 0 x of z plus h of 1 z inverse x of z, and so on. So you can do one more step here, that is taking inverse Z transform. So I am leaving it to you. You can find that what is, if you take the entire equations inverse Z transform, then you will get something y of n equal to something. Okay, so I am leaving it to you. Now if we try to now implement, you see how many delays we require. So z to the power minus 1 up to z to the power minus n minus 1. So that means n minus 1 number of delay elements are required. And if we are tapping out the signals from here, so at this point we are getting x of n minus 1, here x of n minus 2, and so on. Now what are the coefficients associated with this? H of 0 from here, so this is 1, followed by next one we have h of 1, h of 2. So like that we'll be putting all the weights or the filter coefficients, and we need to add them up. So here we have the addition symbol, so that is why we are using adders. So at the end we are getting the output. So in time domain, if you write at this point, you are getting x of n, you are providing x of n rather, and here we need to use the arrows so that it will show the flow of the signal, and here at this point you are getting y of n in time domain. That is how we represent. Now if we take a typical example, so here suppose h of z is given as 1 plus 2 z inverse minus 3 z to the power minus 2 minus 4 z to the power minus 3 plus 5 z to the power minus 4. So you see here the weights or the filter coefficients we have 1, 2, minus 3, minus 4 and plus 5. So these are the filter coefficients. So same process we shall follow. H of z we are representing as y of z by x of z, and then this polynomial, and followed by, if we cross multiply it, so we'll be getting these things. Then we can take inverse z transform. So in time domain we are getting this particular expression. Now if we convert it to the realization or the filter structure, we have a delay line. So maximum what we have, maximum n minus 4, or this is power is minus 4. So that means 4 delay element we require. So we have used 1, 2, 3 and 4. So 4 delay element we have used. So x of n is given as input. So at this point we are getting x of n minus 1. At this point we are getting x of n minus 2. Here we are getting x of n minus 3 and x of n minus 4. Now what are the weights associated with this? So x of 1 is associated with weight 1. Then x of n minus 1 associated with the filter coefficient or the weight 2. Then here we have minus 3, here we have minus 4, here we have 5, and finally we are adding them all, and here we are getting the final answer or the response of the filter. So this is the input of the filter, this is the input of the filter, and y of n is the output or the response of the filter. So that is how the direct from realization is done. So it is very much straightforward, and we can have any kind of filter coefficients associated with it. But now if we want to realize in the linear phase, now this linear phase is having this particular concept, h of n should be equal to h of capital N minus 1 minus n. So this is the primary condition for linear phase that we have already discussed under the FIR filter design, and there we have seen these things. So we have a symmetry of the filter coefficients. So with this, if we proceed, then this h of z for n equal to even, so when n equal to even, we can equally divide them. So from n equal to 0 to n minus 2 by 2 and n by 2 to n minus 1. So in these two part we can divide. Now if we replace n with n minus 1 minus n, accordingly this limit will also change. So now we will have the limit n equal to 0 to n minus 2 by 2, and here also you see that we have the same limit. So That means these two summations we can add up, we can combine these two summations. So after combining these two summations, we obtain h of z equal to summation n equal to 0 to n minus 2 by 2 h of n z to the power minus n plus z to the power minus n minus 1 minus n. So that means here the coefficient, filter coefficient is common pairwise. Pairwise filter coefficient will be common, or in other words we can say that it is very much symmetric. Similarly, this concept can be further taken up for n equal to odd. So for odd values of n, we should have a middle point. That middle point is n minus 1 by 2. So before that we have 0 to n minus 3 by 2. So this is one half and this is another half. And here this is the middle point. So this one we can take outside separately, h of n minus 1 by 2 z to the power minus n minus 1 by 2. Then we can add up these two because of the symmetry. Earlier we have seen that for linear phase realization or linear filter to be linear phase, we should have a symmetry. So following that we are having this kind of symmetry. So for example, if we have n equal to 5, then n minus 1 by 2 is 2 and n minus 3 by 2 is 1. So that means h of z, there we have h of 2, that is the middle point, this is the middle point, and summing up n equal to 0 to 1 h of n, this thing. And if we further if we expand this, we get h of 2 z to the power minus 2 plus h of 0 z to the power 0, that is 1 z to the power minus 4. So it is symmetric. It is symmetric about some axis. Suppose this is your 2, okay, index 2. So h of 2, you can say this one. So this is h of 1, this is h of 1, and this is h of 0. So h of 1, this is 0, here you have 3, here you have 4. So this kind of symmetry we shall have. So let us take an example. So here h of z is given as half plus 1/3 z inverse plus z to the power minus 2 plus 1/4 z to the power minus 3, then z to the power minus 4, 1 by 3 z to the power minus 5, half z to the power minus 6. So by looking at this, by inspection, we can say that n value is equal to 7, and here we have up to n minus 1. So that means up to 6 we have, and the midpoint is 3. So that means this one is the midpoint. So we can take it out, 1 by 4 z to the power minus 3, and we can see that coefficients here and here, these two are same. So we are combining them. Similarly, other coefficients, common coefficients, we are taking together. Now when we realize what we are doing, that since here we have 6, so half of the delay element will be drawing at the front line, upper delay line, and this is the lower part of the delay line. And here for at this point what we are getting, that x of n, and at this point we are getting x of n minus 6. So both of them are having the same coefficient, that is half. So we are combining them. Similarly here for these two we have the same coefficient. So little correction here, we should start it from here. Okay, so this portion is not there. Okay, so from here we are taking the coefficient. Okay, so here also you have taken it from here. So coefficient is 1/3 and so on. So this is how we do the linear phase realization. So how will you understand that whether you have to realize the filter in the linear phase or in direct form, that is by looking at the coefficients. So if the coefficients are symmetric about its midpoint, then only you can go for linear phase realization. Otherwise, you will have to go for direct form or transverse form of structures, filter structure. So we end here. These are the references. You can follow these references. Thank you very much. And in next lecture, we'll be doing that IIR filter structure direct form 1, and 1B lecture will be doing later on. Thank you.